Good afternoon, everyone, and welcome to our second Digital Twin Discovery Series webinar, part of the UK Digital Twin Centre's ongoing mission to make digital twins more accessible and meaningful for UK industry. So my name's Brendan Lowry, and I'm the lead innovation solutions consultant at Digital Catapult. I'll be kicking off this session, so we've got a fantastic hour lined up focusing on real-world applications of digital twin technology in the aerospace and maritime sectors. And we've some guest speakers today. So we've got Andrew Simpson from Spirit Aerosystems and Douglas Kelly from Unusual Technologies. And I'll let those guys do their own introductions later in the call. But they are working on some fantastic use cases, and I'm really looking forward to hearing more. So here's what you can expect over the next hour. First, we'll hear from Andrew and Douglas, as I mentioned, and then we'll wrap up that session with a short Q&A before moving to talk about the upcoming activities in the UK Digital Twin Centre, and Asan will be leading that. But we aim to keep this session kind of relaxed, informative, and interactive, so feel free to use the Q&A feature throughout. But we are quite tight in time, so I'll try and keep everything in check. But just to kind of recap, who am I and why am I speaking? As mentioned, I'm Brendan Lowry, and my role at Digital Catapult and the UK Digital Twin Centre is to support innovators and industry adopt deep tech. And we're looking explicitly today at digital twins. So really to solve complex challenges, improve operations, and unlock opportunities. And today's session is all about how that's being done and how it's being done right now by companies and people like Andrew and like Douglas, who are really leading the way in this space. And at the heart of today's event is obviously the UK Digital Twin Centre, our national initiative co-funded by Innovate UK and the Belfast City Regional Deal. Our mission is really simple. It's to support and help UK businesses, especially SMEs, embrace the power of digital twins safely and effectively. Whether that's through access to tools or experts or collaborative programs, we're here to help make it easier to explore and adopt digital twins. So you've seen the mission on that previous slide. This is the centre. This is the UK Digital Twin Centre. We're a national centre of excellence, but more importantly, we are an enabler for digital twins, and that means really we offer hands-on support for UK businesses of all sizes. We partner with universities, RTOs, and tech partners to bring the latest thinking and research and talent into the centre. We provide access to skilled technologists, centralized tools, platforms, and even lab space to support that early development. And we've also got innovation programs, consultancy, and accelerators, and funding as well. And you'll hear more on that later with Hassan. But today, another part of this story is the showcase and practical use cases. So we can learn and we can adapt from what others are already working on, and that's the kind of point of today. And some of these use cases are with our partners. So we've got partners in maritime operations. We've got use cases in aerospace and defence. We've got use cases spread across different industries. And the point of this is to show that digital twins aren't just theoretical; they're being built. They're being deployed right now, and we're lucky to see some real results with our three partners, and we're very lucky to have Spirit here today. Our first webinar was with Talus, and we've learned a lot from those guys, and we're really fortunate to have Spirit and Andrew here. And the point of this is really to inspire and learn from what these partners have done, and we can see how they went through their journey and take some of those learnings and help you guys in your business adopt them. So as part of digital twins, we look at core technology areas in the UK Digital Twin Centre. Digital twins aren't a single technology. They're a combination of multiple capabilities that work together to create dynamic, intelligent, and trustworthy models of real-world systems. And we've broken them down into 6 key areas. So the first one is cyber-physical asset management. So this is the physical layer. It's the sensors, it's the edge computing, it's the connected devices. So that allows for the real-time monitoring of assets and systems. And then we've got data services. So it's like the plumbing behind the scenes. It is the collecting and storing and processing of large data sets. It enables the predictive analysis and interoperability across all the systems. Then we've got intelligence, and that's where you bring in, the AI, the machine learning, the autonomous decision making. That's where that all comes into play, and that enables a more responsive and adaptive digital twin. And then we've got the UX and visualization. So it's not enough just to build the digital twin; you have to interact with it, and that's where immersive comes in, or dashboards or simulation, and that's that UI UX visualization part of it. And then security and trustworthiness says what it is. We need to ensure that the data is safe, and it maintains its integrity, and we can build systems and dashboards, and everything's we're confident in that because we know it's safe and secure. And then lastly is that integration and interoperability, and that's the glue that holds it all together. So that's our APIs, our middleware, our data pipelines, and the connectors that allow all the different systems to talk to one another. So that was kind of a bit of a whistle stop tour on what the centre is, and there's probably a lot there that you want to hear more on, and we've listened to what the ecosystem want, and I think there is a big push on education. So over the next while, we're hosting some digital twin discovery series. It's a webinar series running through the end of the summer, and it's really just to raise awareness of things like the technologies that I talked about, or the use cases that we're working on. So do keep an eye out for those. But in the interest of time, I do want to hand over to Andrew next. So Andrew is our senior project engineer at Spirit Aerosystems, and he's leading a project focused on jet engine reverse thrusters. It's a highly complex, it's a safety critical component that's used during aircraft landings. So yeah, we're working with Andrew very closely, and Andrew's going to take us through the use case that he's working on. So over to you, Andrew.
Thanks, Brendan. So first of all, I want to introduce myself, and I think there should be slides coming up at any moment, which will give me my cover slide here. There we are. Yeah, thanks, Brendan, for the introduction. Really good to be here. And Spirit as a whole, we're very proud to be one of the 3 founding industry partners in the Digital Twin Centre in Belfast. Very, very excited to be involved in this, the founding of this centre and the setup of these programmes. So I am, as Brendan said, a senior project engineer in Spirit Aerosystems. I've worked here for 10 years, and my background is in systems integration and systems engineering. I'm currently, amongst other things, project managing 2 small programs which are in the Digital Twin Centre. We call them Use Case 1 and Use Case 2, imaginatively. I'm going to talk to you today about Use Case 1, which I'll introduce in the next slide. Introduction to Spirit Aerosystems briefly. We are the largest aerostructures manufacturer in the world. We have sites across the US, the UK, Europe, North Africa, and further into Asia. As a company, we don't build full airplanes. We build pretty much every component of an airplane, but no full airplanes. We build fuselages, wings, tails, stabilizers, control surfaces, helicopter, rotorcraft, aircraft, whatever else. But there's no full aircraft leaves the Spirit factory. Now in Belfast, however, we are Short Brothers PLC. We're fully owned by Spirit, and Short Brothers has a rich history of being the oldest aircraft manufacturing company in the world. And for a period of time, we've been owned by Bombardier, previously Spirit. So both as Shorts and as Bombardier, we did have access into organisations, and we ourselves did produce full aircraft. The last aircraft flew out of our factory in Belfast in the 1990s. So within Belfast, we retain a lot of knowledge and experience on aspects of full aircraft design, which don't exist in many other aerostructures suppliers. Anyone who's in tune with the news just now will know that Spirit Aerosystems is being bought by Boeing, and so the Belfast site is going to transfer to Boeing ownership, and once again, we'll be part of an organisation that does build full aircraft, and so our knowledge and aspects of that history will come back into play again. So on this slide, I'm introducing the use case. We have a past R&D program in which we built a novel thrust reverser for business jets. Now, what is a thrust reverser? It's the final section of an aircraft engine, and parts inside it, including the sleeve and internal doors, pivot or move otherwise to reverse the airflow through the engine during landing. So the airflow that would normally go straight through the thrust reverser out the back is diverted outwards and forwards. This augments the braking of the aircraft after landing or in a rejected takeoff, and it reduces wear and tear and increases performance of the aircraft. However, the thrust reverser itself is a complex, heavy, and expensive bit of equipment. And within Belfast, we have a lot of expertise and experience in building these. We're a world leader in thrust reverser design knowledge, and we're looking at how we can optimize our designs to better meet the requirements of our customers. So in this program, I'll go through the slide quickly. We are leveraging a recent development set of artifacts, both digital and physical, to develop integrated digital twin capability in key product design areas. So we have a prototype thrust reverser, which is shown in the bottom right of this slide, and we have all the digital assets that go into a design of that sort, including CFD, CAD files, finite element modeling, etc., that go into that design. So we have all these things existing, but they're very siloed and they don't really talk to each other. But the question we're asking is how much more efficient could we be if we digitally twinned our physical aspect, our physical test specimen, our actual product, into the digital development assets. So the integration of advanced predictive modeling for the different domains, which is hydraulic, electrical, and systems, to enable virtual testing, and then developing the roadmap for the use of MBSE using SysML, which is a language which can help with the explanation of complex systems in a way which can be intuitive and store data in a way that's not ambiguous. So can we have the next slide, please? Thank you. What I'm going to do in these next few slides is talk about some of the domains that we do our modeling in and how we're trying to connect these together. So the first question really is, what is a digital twin? And there's many different ways of answering that. It's in some aspects it's a bit of a buzzword, but underneath it all there is a really clear, defined meaning, which is easy to understand and makes sense and is a good guiding force. So the definition we're working on is that it's the joining of a physical and a digital asset in such a way that there's real-time two-way communication, command and control communication between the two assets. So if you don't have that communication, what you have is a model and a physical object. As soon as you link them together, you may have a model that's reading data from a physical object, and we may have a physical object that's being controlled by a model. We've had hardware in the loop, and we've had real-time correlation for a long time. But when that communication becomes two-way command and control, then it pivots into being a digital twin. Suddenly you have the two aspects of the system, neither of which is the master and slave, but both controlling in real time. We are starting to see digital twins in use in public-facing organizations, and a good example is SpaceX. During their launches, you'll often see icons on the screen that give an explanation of what's happening on the space vehicle. Much of that information is generated from models which are being updated in real time from sensors on the aircraft or on the space vehicle. And those bits of data are being used to run a simulation in real time, which is then being used to control the space vehicle. So companies are using these in real deployment now. We're looking at how we can use digital twins in the front end of design to lower the cost, timescales, and increase capability of our designs. So with that said, the first question is, how do you connect these assets? How do you connect a digital asset to a physical asset? And a big chunk of the upfront work that we're doing is to try to control our physical test specimens using models which have never been designed previously to do that job. And so we're pulling in software which is very capable of interacting with the real world. And the images on the screen here show some of those models, and the graph in the top middle shows some of the output. So the red line is the expected or modeled hydraulic behavior of a cylinder, which is connected to the green line, which is the generated output being sent to the cylinder controller. So we have, in this case, this isn't reading from hardware. This is fully simulated. So we're creating an output, which is the green line, based on a simulated behavior of the system. This program is at the front end. We have actually now connected this into a hydraulic cylinder and demonstrated that we do have full control and it behaves as expected. So the benefit of an interface, a piece of software like this, is it allows you to run your tests and record your results through a single unified system, which has knowledge of the test it's operating in real time. So it's not a case of press the test button, go away for lunch, and come back and reread your data afterwards. It's in real time. We can see and control the test as it's going. If you have an anomaly, or critically, if you're testing a very, very time-limited event like a burst duct or a fire, you can control that test in real time as it's running based on the expectations coming from a simulation from the digital twin. So if we have the next slide, please. This slide then shows that system on the screen connected to a hydraulic cylinder. Now, it's not massively exciting, but critically, it's showing that using the interface on the screen, we can control the position of the cylinder, which increases our confidence that our modeling and simulation was correct. This is really just the first step towards verification that we have the real-world interfaces. What we wanted to do before we went further with the hydraulic system. Obviously, hydraulic systems are expensive and potentially incredibly dangerous, very high pressures, very high forces. And so we wanted to de-risk before we connect this into the actual high-value thrust reverser prototype. And so we built a scale model. And if we go to the next slide, you can see the scale model actuating. Now, it uses the same control system and the same interfaces and the same communication, but as a 1/3 scale model. So you have the physical scale model here, controlled through an Arduino, which is a prototype electronic board. And the Arduino is acting as a bridge between the physical and the digital modeling. So digital modeling shown on the screen shows the position, and the feedback graph as well shows exactly what's happening, and it correlates to the expected position that's being modeled in the digital twin. So we've got to a stage where we have control of the physical object, a physical twin. And the purpose of this program then is to see how far down the line of integrating our different areas of expertise we can go. And so this slide shows some aerodynamic modeling. On the left-hand side, we've got what's called half models, which is literally just the thrust reverser cut in half. Obviously, the smaller you can create your model, the less computationally intensive it is to run. On the right-hand side, we have quarter models. The half models were used during the production and the certification of the product. We're looking now whether we can use quarter models and then even linearize the quarter models to prevent having to run the CFD in real time, which is a very difficult thing to do. Obviously, CFD is very time intensive and takes multiple orders of magnitude of real time to run the model for a few seconds. So we're looking at whether we can run our CFD, create effectively a table of results based on conditions, and extrapolate between that table, between the lines in the table, to create expected CFD results for a given position when the test is running in real time. This is something we've not done before. We tend to do aerodynamic modeling as part of certification, and there's a huge amount of time to do it. It uses huge amounts of computation, and we have high power computer clusters here and outsourced that we can use. But to be able to linearize the results and run them in real time would be a real change in our capability. I want to talk about how that aerodynamic modeling fits into multi-physics modeling. Thank you for the next slide. So we are now looking at how you build multi-physics modeling and integrate the different aspects of what we do. So the sort of blue lines in the middle of pyramid as such, the inverted pyramids, demonstrates the levels of complexity that we add in. So at the bottom, the simplest, essentially structural model is a kinematic rigid body model, which is a stress tool used to measure stress in the components, but it doesn't take account of things like the flexible nature of some of these aspects, the friction in the different slide rails, and particularly friction due to flexibility can be enormous, of course. It also doesn't take account of the full aerodynamic distribution of forces. Now, one of the targets we set ourselves is to accurately recreate the load stroke curve. So as the thrust reverser is deployed, you saw in the previous slide, the entire outer skin moves backwards. The actuators that do that experience a force, and exactly understanding how much force they're experiencing at each stage of the deployment can help you size those actuators correctly. If you oversize them, you're carrying a huge weight penalty for the life of the aircraft. If you undersize them, you may find that during a rejected takeoff or another extreme event, the thrust reverser deploys more slowly than expected, which can have a performance impact, which isn't desirable. So sizing them correctly is critical. So the question is, how do you simulate the load stroke curve? And we have different approaches to that. We can use the finite element models, which need to be quite complex, or we can use a very, very simple back of the envelope calculation where you assume a uniform distributed load on the moving components, which gives you an answer. It's not fully accurate, but it's often close. Or you can do CFD, which we have done in the past, as you've seen, and the CFD can give you more accurate results, but it's very computationally intensive. So we're looking at, can you do a multi-physics model which incorporates all these things into a single model, linearizes them, and can give you decent results. So as you move up this inverted pyramid, first we start integrating structural GFEMs and legacy qualification test data. So we'd be correlating them against test data that we have from an engine run test stand. And then near the top, we're going to be bringing in CFD data to actually correlate against a huge number of cases that you can run in CFD without having the test stand and an engine sitting in a field somewhere. And at the top, we're going to bring in the actuation system model, which is what I showed you in the previous couple of slides ago, the actuation system model demonstrating that we're actually modeling the hydraulics and the behavior of the system as a whole. This is an R&D program. Much of what I'm describing here is work that has been done in a way in some areas of industry in other fields, But as far as we're aware, in the design and development aspect of an aerospace program, this hasn't been done to this level at all. Certainly, certification authorities haven't seen this. They've not seen integrated modeling. They're very used to siloed modeling, where each discipline sits by itself. So we're exploring how far down this route we can get. We're hopeful we can get to the top level. We're hopeful that we can end up with a model which encompasses all the physics that we normally analyze and produce, but we'll see how far we get, and it's an exciting program. If we can go to the last slide, then it's simply a graph that shows where we are now as of today. So there are two lines in this graph. The darker blue line is a static finite element model with no gravity included. It's kind of the simplest we can do to have an accurate structural model, and using a uniform predicted load on the moving components, this is a load stroke curve prediction based on that model. And then the purple line, which has fewer points on it because it's done with CFD, which, as I said, is computationally intensive. The purple line is the deployment of the thrust reverser with the loads calculated in CFD. You can see they're well correlated. It's a good place to be starting. Those two lines match each other to a point where, honestly, the differences are less than you'd see in the scatter of a test program. And so we are happy that we do roughly understand what's going. There is a bit of behavior difference. There's a knee in the curve towards the right-hand side, and that knee is being predicted in a different position. That's interesting. We're not quite completely sure why our two models are predicting that knee in a different position. What we'd like to do is move that to one line where the data is coming from one program, one model, and that model is linked to the real world. So when we see the knee in the curve, we should be able to measure it. We should be able to have strain gauges or LVDTs that are coming back, or load pins coming back, telling us exactly the load that we're getting and simulating that load and seeing the data matching up exactly. If we get to that stage, we believe we can reduce time, reduce costs. Cost and time are closely related in a development program, and critically also produce a product which is more closely matched to our customers' requirements, and perhaps even exceeding the requirements, going beyond simply matching requirements into the realm of the optimal design, the best design that can be produced to satisfy what's happening. That's the end of my slides. I'm looking forward to the question and answers later, and please, if you have questions, put them in the box, and I know that Brendan will receive those questions and we'll discuss them later on. Thank you very much. Back to Brendan. I'm sorry, back to Asan.
Thank you, Andrew. And thank you for the insightful presentation. We'll have, like Andrew said, we'll have a question and answer session after our next session. So if you have any questions for Andrew, you can share them in the Q&A box, and Andrew will share them. Andrew will answer them later on. Now on to our second session, which is, and we'll have Douglas Kelly, who is director at Unusual Technologies. He's going to be presenting the amazing work they are doing in the space of digital twins of oceans. Over to you, Douglas.
Hello. I think that should be me sharing now. Okay, so I'm Douglas Kelly, and I'm the director of Unusual Technologies. To start off with, I'm going to give a brief description of what we do. We work in a range of different industries. Some examples here: academia, arts and entertainment, and corporate. Though there's not really any specific industry we focus on. The kind of work we do is software development for various needs, and they fall into these three areas that we see in the center of the slide. So when someone needs software development that has a graphics and data visualization need, in other words, making it pretty, or when they need software that has Web3, new technologies, anything sort of cutting edge. In the past, that was things like VR, AI, AR, blockchain, and nowadays it's more AI focused. Or when they want software that has education, training, and gamification needs. So we see ourselves as pedagogical designers who are good at doing software that's either training or delivering maybe a thought-provoking message or maybe a marketing message. So if you're sort of familiar with digital twins, you might think you might recognize how some of these skills can be used in making digital twins, and that is a big part of what we do. But it's not exclusively what we do, but is a large part. And we're going to talk to you about some digital twins today. The first example I want to give. We're going to just do this shortly, just to give a sort of quintessential digital twin example. Is Lost Horizon. This is a nightclub in Bristol. In the top right of the slide, you can see the physical venue there. And during COVID, they wanted a way to get a 3D model of their venue and bring it into, in their case, virtual reality, so that people could visit and still continue to enjoy concerts even during the lockdown. But it has other applications outside of COVID with people with disability or maybe a geographic reason why they can't access a concert. And what happened there is in the real world, they would stream in performers. So in the bottom left, you can see they get this stream of a DJ, and they bring that into the virtual world and have that, as you see in the bottom left picture. So there's a real-time version of the concert going on in this virtual world. And they also played with other concepts like having screens along the walls where in both the real world and the virtual world, where people can wave to each other and communicate with each other, whether they're in the live event or in the virtual clone. So that was a quick sort of fun entertainment example of a digital twin, but the main thing I want to talk to you about today is OceanX. So first, a description of who OceanX are. They are, as you see in the box, they're a global organization that are all about exploring the oceans, and they've got sort of two arms to do that. They've got scientific research where they're looking to learn all about the ocean and understand it better, and educational arm where they're looking to take that information and share it and make it more accessible to the world. And ultimately, they're looking to safeguard the ocean into the future and make sure we're all looking after that resource properly. So the way they do this is by collecting information, and they have very high tech, lots of cool gadgets to do that. So it's lots of sensors and information. They've got the ship in the top right there. They've got a submarine. They've got ROV, which is an unmanned submarine, and all this cool equipment. You can see in the bottom right, the sort of Star Trek-like interior of all this gear they have. So they even with all this equipment, they struggle to deal with the major problem that anyone who's studying the ocean has, which is the vastness of it. So to get around that, because you need really like thousands and maybe even more than that of these vessels to be able to get information about the whole ocean. So to get around that, they started looking at using AI to make predictions about what's areas they've not yet explored, what's likely to be there. And what's more interesting is they also have a sort of confidence level. So if they've not explored an area, they can make a prediction on it, and they can also make a confidence rating to say how likely that prediction is to be accurate. And that means that the areas that are not very accurate, they can use that to inform the missions of their actual ship, and they can aim their missions to explore those areas, which means they're bringing that data in. They're getting the real data to say what's actually there. Whether the prediction was right or wrong, it now gets corrected and more confidence, and they can start to make further predictions, better predictions, and you get this positive feedback loop where we start to train this model that's really good at understanding what's likely to be places based on the information it has. So we've talked about that as basically the issue of the vastness of the ocean and how we can use AI to solve that. But now we're solving that with AI. We come across this next problem, which is now we have vast amounts of data and no easy way to process it. So we can start looking, this is where digital twins comes in. We can start looking at how digital twins can help visualization of data and how it can make that a much more intuitive thing to do. So as human beings, if we take an example of looking at data like terrain, rock formations, as human beings, we find this very easy to use our eyes to see things in 3D and understand it. So by creating a digital twin of that, it's very easy to get this information out to scientists or anyone using the program. The other thing this does is it allows so in the past they would have used graphs and charts and stuff to understand the terrain and maps. But if they're doing that, if you imagine a geologist studying this terrain and these formations with these charts and so on, they're only looking at the data they need. But if we're having a digital twin that's a 3D visualization of this, it's not too much cognitive load to include other data like marine life. And what we're hoping is that will allow future scientists who are working on maybe an area like geology to see something like marine life and start to have a holistic view of it all and see maybe patterns or make new discoveries that they might not otherwise have made if they just had that information in isolation. The other thing the digital twin does is lowering the barrier to entry. So a big part of OceanX, like I said, is to try and educate the world on what's going on with the oceans. They want policymakers to understand for policy they're writing and laws, and they need to help them understand in an easy way of showing them the information they're discovering. And digital twins help with that. And also, if you consider the sort of next generation of children, getting them interested in the ocean and lowering the barrier so they feel it's something they can all get involved with. So without further ado, I'm going to play a demo. This is a demo that we made back for a conference in June, the United Nations Ocean Conference in Nice, France. And basically, this was a proof of concept that we made for that conference, but also at the beginning of our journey with this project. We needed to have something that my development team and the OceanX science and research team could all understand and agree on as a sort of future direction that the project's going to aim towards. So what you'll see here, this imports real data from a real dive they did. You can see that line there playing right now. That's the actual track that the submarine followed. This is a video, so you're not able to interact with it, obviously, but there is the actual, at the conference, there was interaction capabilities where you could explore within the bounds of the dive, you could explore yourself. And as I said earlier, later on, we're going to use AI to make predictions and allow you to explore outside of the bounds of the data they actually collected there. Now I want to move on to the problems with the project and the things we are working on now. This is worth talking about because I think if any of you, the audience, are interested in digital twins and you're at the early stages, I think it's worth you understanding it's not just a development project, but there's a huge amount of design that goes into these. We talked earlier about the terrain visualization, how that's easy and intuitive to do, but there's lots of data that's not so intuitive. So an example would be like temperature, how you visualize temperature. I think people might sort of, their gut reaction might be to say, well, you can have a sort of red-blue spread and you can see how the temperature changes that way. But if you consider this in 3D, if you're in there and you see a big red cloud in front of you, it's going to be very difficult to see past that and see that maybe it changes, becomes more blue within a kilometer or whatever else. There's also other issues like this. It's not just temperature, but there's many other things that we don't normally see with our eyes that are hard to visualize, like salinity. And if you choose salinity again, you could have a color, but then you start to soon after you go through all these variables, you start to run out of colors, and how they merge together doesn't look quite right. So there's a lot of design problems that go into this. And as I say, if you're considering a digital twin yourself, it's worth considering that the development team, in our case, we sort of become mini experts on our niche topic matter that we're exploring and working with. And we're currently still running through interviews with different scientists and people who will be using this data to make sure we're understanding their needs and we're going to be able to create something that addresses all of those. Okay. So I'd like to finish up by talking about some sort of broader aspects of anyone who's considering a digital twin and thinking about these three main aspects that might suggest you might need one. So there's removing the danger. If you're familiar with submarines in recent years, I think there's sort of bad press, but you can see how they can be very dangerous. OceanX are a sort of different league there, different level in their sort of quality and safety measures, but there's still always inherently danger with going out to sea in any way. So by being able to create a digital twin, you reduce the need for many journeys. People don't have to experience things firsthand. They can have one expert elite team go out, gather the data, and bring that back to the masses. You can also think of it in terms of factories and heavy machinery. There's oftentimes people make digital twins for training in these areas, where obviously if you're training, you're more likely to run into danger and to make mistakes. And this also feeds into this next one of cost. You're likely to damage the equipment or to damage yourself. But having a digital twin allows you to do this at lower cost, lower risk to the equipment, lower risk to yourself, and get that initial part of your training done. And then finally, providing easier access. So again, if in the instance of OceanX, having a ship go down, collect this data just once, and then theoretically anyone with machine around the world all at once can view this data. So you can have something where maybe very expensive equipment means only a few people can use it, and suddenly through the magic of digital twins, you can have many people accessing this. So I'll finish up there and say thank you for listening. If you're interested in any information about software development for your projects, especially digital twins, but anything else really, here's our information. Feel free to get in touch with us via our website. Also, we'll be around for this question and answer session. And I'll hand you back over to get that started.
Thank you, Douglas. Andrew, if you can come on screen as well, we'll start taking some questions. And I'll just start with the question of, and this is directed to both of you to some extent, is how important do you think that especially in the current scape, digital twins are in both aerospace and maritime sectors? Andrew, if you can go first.
Yeah, sure. I think they're becoming more important. I think we're moving towards a phase where to ignore the integration, the potential benefits that the integration of physical and digital can provide us would be to ignore massive potential savings in development programs and in operation. So most digital twins that we see now are focused on the operation end where there are huge gains to be made. The organization I work in obviously is focused on design and development. And so we're looking at how we apply the same knowledge and learning into that area. We haven't seen yet the full potential of what can be gained with integrating these models and these concepts of digital twins into our design process. But we're very aware that as with the change from paper drawings to CAD in the 1990s, there's a step change coming towards us. And being on that wave is very, very important. We have to understand the technology, we have to implement the technology and gain what we can from it in our organization.
And Douglas, for you on the maritime.
Yeah, I'll start even broader than maritime. As I said in my discussion, we aren't any one industry specific, but we sort of become experts in the area we're focusing on. And we're still early enough in this. I wouldn't like to call myself an expert. We're about 3-4 months in, but where my expertise does lie is within that sort of pedagogy and training aspect. And it's huge for that. And I think this is why it's really useful for something like the ocean, where people don't really understand what to expect. You know, you can only watch Little Mermaid and dream of what might be under there. So you need things like digital twins to help people understand and be able to start training, whether that's like piloting a submarine or understanding the sort of science and the things that are going on there. It's a really nice tool to bring people quickly up to date with what they need to know when exploring unwell understood areas like the ocean.
Awesome. I have these two questions and I'll combine those and Andrew, they're for you. They're from David and Alireza. The first part of the question is small and he's asking if CFD means computational fluid dynamics.
Yes, sorry, I maybe should have clarified that. Computational fluid dynamics, yes.
And the second question is, can you please explain the list of softwares you are using for your model-based system engineering? He said that it looked like Skimscape, and if there is a possibility of API API integration with your system? And if so, if there's any requirement management that is required for that?
That's a really interesting question. I'm not free to give you a full list of all the software that we use for every aspect of what we do for obvious commercial reasons. But yes, the screenshot on the first major slide was Simulink, and we're using the MATLAB MathWorks environment quite extensively. For a lot of the other software, we're using software from PTC, ANSYS, and others, many others. So we have a broad range of software. And as I said a few times, traditionally we've been very siloed, where departments and even teams within departments choose the best software for what they are doing without really considering the integration across the wider field, because we haven't had that integration. And this is where we're trying to achieve the real gains now, is by integrating the software. The question about MBSE, we are using MBSE tools. We're not using MathWorks tools directly for MBSE. That was system simulation, where MBSE we're using currently for requirements management and program planning and program and project data storage and sharing. We are using SysML for that, although we're still exploring which package is the most appropriate for us. It's not something that we as a company have invested in before, so we're learning as we go on that topic. APIs, I believe one of the major aspects of what the Digital Twin Centre in Belfast is going to be working on is the development of application layers and communication between applications. So we are not going down the route of developing APIs yet. We are working on a case-by-case basis to try and make our models talk to each other. I know that the Digital Twin Centre has a very developed concept for a digital twin as a service, which involves layering different bits of software through open communication protocols. We're very interested in that. We're going to learn with everyone else as that progresses. We're looking forward to the results from it. I think that was 3 or 4 different aspects of that question, so I hope I got them all.
Thank you, Andrew, for that. There's a very interesting question around the security and trustworthiness of digital twins, and it is directed towards Douglas. And it's around, do you restrict access to digital twins data visualizations according to who is wanting to use to protect from bad actors? For example, underground cable security, illegal fishing, pirates, etc.
Yeah, exactly that. Yeah, I think so. So a lot of countries work with OceanX to explore their seas, and generally they don't want that fed into the public domain. So it depends who's funding it. They, as a sort of a charitable organization, will try to get the data out to as many people as possible. But obviously, if they're being commissioned to come in and find something, I think a recent example was like the fjords of Norway. I don't think they want anyone knowing a map of how all their fjords work. So that's all kept secret. There's 2 different layers to that. There's being able to actually visualize it, or whether we can even use the data for training or not. And both layers are both things that get negotiated about whether we're allowed to use that in overall data.
Awesome. I'm just wary of the time, and again, I'll wrap up the question and answer sessions here. I know I have some other questions as well, but thank you very much, Andrew and Douglas, for your insightful presentations. I'll quickly share my screen.
Yeah, thanks for the invitation again, Hassan. It's
Yeah.
been appreciate the opportunity.
Thank you very much. Cheerio.
Can you guys see my screen? Just if anyone can let me know.
Yes, all good.
Awesome. So hi everyone, my name is S. Mukhtar and I'm the Innovation Manager at the UK Digital Twin Centre, and I'm excited to take you through an overview of what we offer and how you can get involved. Let's begin by understanding the journeys we are supporting. Brandon briefly touched upon a few of them. But for companies who are trying to understand digital twin better, we have sessions like this, where we have webinars and master classes. For companies who are further down the line and want to create proof of concept for an idea, we have our accelerator program. And lastly, we have labs and real world environments for more mature companies. And again, at the heart of all of this is our belief in partnerships. We are actively connecting SMEs, tech vendors, industry leaders to encourage knowledge sharing and unlock new commercial opportunities. And one of the first touch points for you guys and for all the organizations is our readiness assessment. This tool helps you, in fact, identify where you are in that journey and how we can best support your next steps. It's quick, insightful, and a great way to map out a potential collaboration path with the UK Digital Twin Center. I'll keep the slide up for 5 more seconds. So if you want to take a picture and go to our readiness assessment. Okay, so if you're just starting your journey and want to know more about digital twins and how it can help your business, we have multiple interventions and events. One of them is this webinar. We are also hosting networking events where you can meet like-minded innovators, potential investors, and collaborators. These events are focused on building value and showcasing real-world applications of digital twin technologies. We recently had our one of our events in London, and we are hoping to do our next event in September in Bristol. So keep an eye on our social media as we confirm the date. All of these events lead up to our accelerator, which is now called Digital Twin Adoption Program. It is for pre-formed teams of an SME industry adopter and tech vendor to work together on a proposed digital twin use case and build a proof of concept within 7 months, with support from UK Digital Twin Center and a funding of 100K. Open call for this program is set to be announced in August, and we will have office hours throughout the open call process for any application guidance. What are the benefits of it? We offer a suite of opportunities and offerings. Mentoring support from digital twin experts. We have in-house technical supports. We have technologists who will be supporting you throughout the duration of the program. Like I said earlier, we have funding support available of £100,000, and that will be distributed as per the development plan that you will submit to us. You'll have access to Digital Twin Center and the lab facilities that we have, opportunities to present to investors and other stakeholders at the events that we'll be hosting, and access to our extensive digital catapult network for partnerships and growth. And who should apply? And we are looking for a very particular set of companies. We are looking for teams that bring together two key players. One, SME technology vendor. This is a company who is providing or creating digital twin solution, particularly in one of those 6 areas that were mentioned by my colleague Brandon. And then an SME adopter who is looking to integrate those solutions into operations. Both companies must be registered in UK, and ideally industry adopters should operate in sectors including maritime, aerospace, or defense sectors, or how we internally like to call it, MAD sectors. While technology vendors should specialize in one or more digital twin technology areas. This collaboration will ensure practical, high impact use cases that deliver real world value. And how we are going to be assessing your applications. Firstly, making sure that they are unique and impactful, and on the quality side, making sure that they have the strength and alignment of your partnership. In terms of feasibility, how realistic and achievable your project plan is. And on the impact side, the commercial and operational benefits you aim to deliver. And then we'll also see the alignment with MAD, maritime, aerospace, and defense sectors. We want to fund projects that are not only pushing boundaries, but also demonstrate clear value with the industry. If this sounds like an opportunity for your business, we encourage you to apply and become part of this exciting journey. We have another accelerator which will come later on in the year, I think around September timelines, which will be more focused towards R&D, research and development focus, and it is designed to engage academia in solving complex industry challenges. These challenges will be identified, in fact, by our industry advisory panel, which includes leading tier 1 companies in aerospace, maritime, and defense sectors. Once the challenges are published, academic institutions and research technology organizations will be invited to propose solutions. This is an opportunity to apply cutting edge research to real world problems with tangible industry relevance. And as part of this accelerator, also successful applicants will receive funding support to carry out proposed projects. Again, if you're interested in learning more or want to get involved in any of our programs, we encourage you to sign up through the link provided. This is your great way to accelerator, funding opportunities, events, and much more. I would like to thank once again Andrew and Douglas for joining and for sharing such exciting presentations. And I would like to thank everyone who joined us today. We are incredibly excited about what lies ahead for the UK digital twin ecosystem, and even more so about the role you can play in shaping it. Have a lovely afternoon, and that's all from us at UK Digital Twin Center. Have a great day. Bye bye.